Imagine you're an engineer at a university and you want to be able to connect all of the university's buildings via some fast network. Basically, between any given pair of buildings, you want to be able to put some super fast internet line that can transfer data between them. You don't necessarily have to have data lines between every single pair of buildings. You only have to make sure that there exists some path between any pair of buildings, whether it's direct or indirect. For example, let's imagine these are the buildings at my university. And let's imagine that, so the nodes are buildings, and then edges are possible ways of connecting two buildings using some high-speed internet wire. So between any given pair of buildings, let's say that the edge weight is the cost it would take to build a wire between these buildings. I don't necessarily need every single pair of buildings to be connected. All I need is for there to be some way to get from one building to any other building, even if I have to traverse between a bunch of different buildings along the way. So as an engineer, I not only want to build such a network, but I also, as a, kind of someone that's an employee of a university, I want to minimize the cost, right? I don't want to make the most expensive possible network. I actually want the least expensive possible network. So it turns out that this network designing problem can be formulated as finding a minimum spanning tree in a network. That's a lot of words that I just threw at you. Let's start with something simple. So first, I have to discuss what is a spanning tree. So given some graph G, for example, this is my graph G, a spanning tree is a subgraph that contains every single node in G. So it has every node in G. It contains a subset of the edges in G. So every single edge in my spanning tree must have existed in my original graph. And it has no cycles, and it is connected. So these two definitions, these two requirements, these are just the definition of a tree, right? A tree is by definition a graph that has no cycles and is connected. Technically, it's no undirected cycles, but regardless, in this case, we just need no cycles because we have an unweighted graph. An undirected graph. Okay, so what would an example spanning tree of this graph look like? Well, it has to contain all of the nodes of G. So let me use a different color. I'll use pink. So it has to have all of the nodes of G. Oops. Okay, so it has all the nodes of G. Oops, I was missing one. There we go. It contains a subset of the edges of G, but this subset of edges, I have to have no cycles, and the resulting graph has to be connected. So for example, let's say I put this edge, I'm just arbitrarily picking edges, this edge, and for example, this edge. This is a subset of the edges of G, and this graph does not have cycles, but it's not connected, right? There's no connection between this component and this component of my graph. Therefore, this is not a spanning tree. This, however, So this, however, is a spanning tree because it's a subset of the edges of G, it has no cycles, and it's connected. If I were to add an edge here, this edge, for example, this would no longer be a spanning tree because it has a cycle. So that would not be allowed. And similarly, if I were to build an edge like this, this would not be a spanning tree because, well, A, it has a cycle now, and B, it's not, so this edge didn't exist in my original graph. Every single edge in my subtree must have existed in my original graph. In my spanning tree, sorry. So let's just reiterate, this is a valid spanning tree of this graph because it contains all the nodes of G, A, B, C, D, E, F. It contains a subset of the edges of G, so every single edge that appears in this spanning tree also appeared in my original graph. It has no cycles, that's correct, and it's connected. So this would be a valid network in my original network building problem. However, remember that ideally I want to minimize the cost that it takes me overall. So the problem that I want to potentially solve is, out of all possible spanning trees, so out of any possible subgraph that I could create that holds these four properties, which one has the lowest total weight, the lowest sum of all of its edge weights? That would be a minimum spanning tree.